Chapter 6, Section 3. Conditions for parallelograms. In this section, our objective is to prove that a given quadrilateral is in fact a parallelogram. We're basically going in reverse from the Section 2 video. Who uses this? A bird watcher can use a parallelogram mount to adjust the height of a pair of binoculars without changing the viewing angle. Let's look at a few conditions. If it's a quadrilateral with a pair of opposite sides that are parallel and congruent, then it's a parallelogram. Notice the same sides are parallel and congruent. The next one, a quadrilateral with opposite sides congruent means it's a parallelogram. The opposite sides are congruent to each other. Therefore, it has to be a parallelogram. If the quadrilateral has opposite angles being congruent, then it is also a parallelogram. AC is congruent to BD. It's a parallelogram. Let's look at a proof. We're given that segment KL is parallel to segment MJ, and segment KL is congruent to MJ. Prove that JKLM is a parallelogram. Well, the first statement that we have here is given to us. We can see that right above here. So we know our reason is the given. The hint they're giving us is that the reason is for the next statement is alternate interior angles. So, alternate interior angles, if this side is parallel to this side here, and JL is our transversal, we can see that angle 1 and 2 are going to be our alternate interior angles. The third statement, JL is congruent to JL. Well, we know that based off of the reflexive property. We now have two sides, another set of sides, and a set of angles are congruent. So we can state that this triangle up on the left side here and on the bottom right hand side here, both of them are congruent to each other. And we know this based on side angle side. A side, an angle, and then this side here. This side, an angle, and that shared side. Once we have that the two triangles are congruent, we can state that any of the corresponding parts are congruent as well. In this case, we want angle 3 and 4. So, angles 3 and 4 are congruent. This enables us to state that JK is parallel to LM. We're basically using the backwards version of the alternate interior angles. If you recall back to chapter 2, when you do that, you're using the converse. So it is simply the converse of the alternate interior angles theorem. Let's look at 7. 7 is the last statement, so we know that that is what needs to be our proof. So, JKLM is a parallelogram. However, the big question is why? Well, now that we've deduced that JK and LM are parallel, we have two sets of opposite sides are parallel. So based on the definition of a parallelogram, JKLM is a parallelogram. Let's look at a few more. If you have a quadrilateral with angles that are supplementary to the consecutive angles, then it's a parallelogram. Notice how if you were to have added these two together, they'd be 180, and if you were to add these two together, you'd have 180. Well, corresponding angles are supplementary, so therefore it has to be a parallelogram. And in this one here, we have a quadrilateral with diagonals bisecting each other, means that you have a parallelogram. Notice that BZ is congruent to DZ, and AZ is congruent to CZ. The two diagonals cut each other right in half. Let's try applying this property. show that ABCD is a parallelogram for x is 7 and y is 4. We can use simple substitution for this. So if we replace x with 7, we see that this side is 21. And if we replace x with 7 on side AD, we see that 7 times 3 is also 21. So we have one set of opposite sides are congruent. But for this to be a parallelogram, we need to know that the other sides are congruent to each other as well. Let's see if this happens. Well, substitute in 4 for y. So 2 times 4 is 8, and 8 plus 8 makes 16. If we substitute 4 in for y and AB, we have 5 times 4 minus 4, which is also 16. So we have opposite sides are congruent. Therefore, it's a parallelogram. Take a moment and try this next one. Now that you've had a moment to try this next one, let's see if you guys follow with the same steps that I did. We have consecutive angles here, and we know that consecutive angles must add up to 180 degrees. Or you can also notice that if you plug in for these two angles here, they have to be congruent. So let's try a few different things here. We have z is 11, so we have 9 times 11 plus 19. This gives us 118. We can do that for this side as well. We have 11 times our substituting in for 11 here. So 11 times 11 minus 3. That is also 118 degrees. Well, if we use the fact that w is equal to 4.5, we have 14 times 4.5 minus 1 is 62 degrees. Well, we have a set of opposite angles are congruent here. We don't quite know what E is, so we can't necessarily state that that one is 62 unless we use the fact that we know that the interior angles are 360. Might be easier to just use consecutive angles. So 118 and 62, they in fact give us 180. So yes, it is a parallelogram. Let's apply some conditions for parallelograms. Determine if each quadrilateral must be a parallelogram. And then let's justify our answers. This first one here, is it a parallelogram or is it not? Based on the information, not whether or not it looks like a parallelogram. In this case, the answer is no. It does not meet the conditions of a parallelogram. How about B? If you look at B, you notice that you have diagonals bisecting each other. So therefore, yes, it is in fact a parallelogram. Let's try proving parallelograms in the coordinate plane. For this example, show that quadrilateral ABCD is a parallelogram by using the given definition or theorem. This is when you really need to pay attention to what the question is asking for. In this case, it wants you to use the definition of a parallelogram. So start with plotting each of the points. Now that you've plotted each of the points, we're going to use the definition of a parallelogram. The definition of a parallelogram states that opposite sides are parallel. So to decide whether two segments or lines are parallel, their slopes must be the same. So let's find out what the slope of each of our sides is. AB, our change in y is 1, 2, 3, 4, 5 over 1. For B to C, our change in y is down 1, 2, 3 and over 1, 2, 3, 4. For CD, we're going up 1, 2, 3, 4, 5, and over 1. And for AD, we're going down 1, 2, 3. So our change in Y is 3. And our change in X is 1, 2, 3, 4. Notice the slopes of our opposite sides are the same. Therefore, this is a parallelogram. Try the next one. For this one, the work and the answer will appear momentarily. If you notice, the slopes of GH and JF are the same, and the distances of GH and JF are the same. Therefore, figure FGHJ is in fact a parallelogram. It might be helpful to have a lot of the pieces of information all in the same place. Take a moment and add these to your notes so that way you have quick reference to each of the theorems. That concludes the section on conditions for parallelograms.